last lecture of our design of steel structure. Okay, so in the last lecture, we will discuss up to our beam to beam connection, in which we have to design for bolted connection if our main beam is connected with one secondary beam, or our main beam is connected with two secondary beams in our second example. Okay, so students, after bolted connection, now the turn for welded connection. Okay, so welded connection is also a revision of your elementary structural design subject, in which there is a chapter number 3 which is welded connection. So in IS codal provisions, welded connection is given on page number 78, 79 and 80. Okay, so in welded connection, there are two types of examples which is in your GTU exam point of view. Okay, so in today's session, we will discuss up to our two examples of welded connections. Okay, so now let us start our welded connections. First example, it is a welded frame connection, and in welded frame connections, our first examples type is double plate frame connection. Now double frame plate connection, it means this is our plate, IS angle plate. So you can see that this is steel column. Okay, so this is your side view and this is your steel beam. Now if we are seeing this component from the top of the view, so it is already discussed that this is front view. Then if we are seeing it from the top of the view, our steel column will be like this. Okay, this is flange portion, this is web portion and this is flange portion. Now this is steel beam. So if we are seeing at the top of the view, okay, so in this top of the view we can see only flange portion, because we have to provided this plate. So a flange portion is hidden in this figure. Okay, now if we are providing IS angle on both the sides of wave of a beam, then it is a left side corner which is seen behind of this portion, and this portion will be like this if we are seeing from the front side. Okay, so there are two types of load. First one is shear force. So generally shear force is generated at the junction point. Okay, and second one is bending moment. So you all know that bending moment is force into perpendicular distance. So we will get our answer of bending moment. So in this example, we have to check what is the length of welding whenever the force is x value and bending moment is y value. Then the question is an ISLB 400 beam. It means this is our ISLB, Indian Standard Large Beam 400 beam, is to connect an ISHB 300 column. So students, this is our ISHB 300 column at 576.8 Newton per meter to transfer an end reaction of 200 kilonewton. It means our beam transfer 200 kilonewton load to our columns. Okay, now the question is design double plate welded connection. It means we have to provide it two plates on both the sides of the beam. Okay, so you can see that our load which is acting at the junction point is 200 kilonewton. So our first step is to write down shear force is equal to 200 kilonewton. Now we have to assume that our size of this plate. Okay, so say for example we have to assume that our size of this plate is 50 cross 50 cross 10, or 60 cross 60 cross 8. But in this example we have to assume that using 50 wide plate, it means this width is 50 Now load is generated over here and this length is 50 So load into perpendicular distance, which is our bending moment. So our bending moment which is generated at this end is load into perpendicular distance which is 200 into 10 raised to 3 because 200 is in the unit of kilonewton. So 200 into 10 raised to 3 into 50 because this distance is 50 mm. So at this point our bending moment generated is 10 into 10 raised to 6 Newton into mm. Okay, so this is 10 into 10 raised to 6 Newton into mm. Now we have to assume that if this length, our provided length is 50 mm, now what is the thickness? Okay, so first of all we have to find out the thickness of plate provided. Okay, so you can see that our ISLB 400 which is our beam having connected with web portion. Okay, so first of all our thickness of plate is 8 mm which is find out from steel table. So all the students are moved to page number 79. So, sorry, page number 80. So, on page number 80, our first figure indicate that if this length is 8 mm, then our another length, which is the length of weld, is 1 point thickness. So, this thickness is 1.5 mm more. So, you can see that the thickness of plate should be 1.5 mm more than the wave thickness of the beam. Okay, so this specification given from this side. So our total thickness of plate is 8 plus 1.5. So it is 9.5. It means we have to provide our plate thickness in such a way that it can resist 9.5 mm thickness. So therefore we have to use 10 mm thick plate. Okay, now you all know that there are two types of welding connections are there. First one is field weld and second one is shop weld. Now you have to find out the value of field weld and shop weld. So it is called as design strength in weld. So students, this equation is given on page number 79. So you all the students are moved to page number 79 in which a close number 10.5.7.1.1 called as fillet weld. So you can see that this is our fillet weld. So for fillet weld, the design strength equation is FWD. D means design and Fw means strength of weld. So design strength of weld is Fwn divided by gamma Mw. Now what is the value of Fwn? So you can see that the value of Fwn is Fu by root 3. Now root 3 is constant. Fu, so you can see that what is Fu? So Fu is smaller of the ultimate stress and it is 99 percentage, it is 410 megapascal because the plate ultimate strength of plate is 410 megapascal. So students, our Fu by root 3 value is put down in this equation and we will find out the value of Fwd is equal to Fu by root 3 into gamma Mw. Now your Fu is 410, root 3 is constant. Now as discussed earlier that there is two types of weldings are there. First one is soft welding and second one is field welding. So the value of gamma Mw which is the partial safety factor for welding is given on page number 30. So you can see that for shop welding the partial safety factor is given as 1.25 and for field welding the partial safety factor for welding is given as 1.5. Okay, so if we are putting both the values then the value for shop welding is 189 newton per mm square and for field welding it is 158 newton per meter mm square. It means if we have to provide it 1 mm weld then it can resist this load. Now you can see that in this figure this is a B point and this is a A point. It means how much length of welding is required at this point and how much length of welding is required on this side. Okay, so first of all we can design at B point. Now you all know that at B point a bending moment will be generated. So what is the value of bending moment? It is given in the question, and after that we have to find out it is 10 into 10 raised to 6. Okay, so first of all whenever you have to design for welding, then you have to assume that the thickness of welding, so minimum size of welding is given on table number 21. So you can see that minimum size of welding is in which range. So if our thickness of thicker part is over and up to 10 mm, then our minimum size of welding is 3 mm and maximum size of welding is, if we are providing 10 mm plate, then our maximum is 8.5. So our size of weld is in the range of 3 to 8.5, but we have to assume that our welding size is 6 mm. Now, if our size of weld is 6 mm, then first of all we have to find out minimum throat thickness. Now, minimum throat thickness is assumed as TT. So the equation of minimum throat thickness is 0.7 into S, in which S is the size of weld. Now, if we have to assume that size of weld is 6 mm, then our answer of minimum throat thickness is 4.2 mm. Now, you all know that the equation of bending stress FWT is M by Z. Okay, this is from mechanics of solid, in which stress is equal to M by I is equal to F by Y. Okay, so from that term our bending stress is M by Z. Now M is moment, but Z means modulus section. Okay, it is section modulus, and section modulus is BD square by 6, because it is I by Y, and for I it is BD cube by 12 and Y is D by 2 or B by 2. Now our plate having a width of L and thickness of T, so for BD square by 6 our Z term is TT into LW square by 6. Okay, so after putting value of Z is equal to TT into LW square by 6, our equation will be like this. Now 6 is constant, M is 10 into 10 raised to 6, TT means 4.2, then we have to find out our value of LW, because our FWD is 158. Okay, it means if we have to resist a moment of 10 into 10 raised to 6, then we have to require the length of welding is 212.62 mm. Now at the end you can see that this is length. Now this is called end return. Okay, so the equation of end return is 2 into S, so we have to provide it end return of 12 mm. Now this length welding is done. Now the turn of welding at A, so welding at A is subjected to shear force of 200 kilonewton. Now for shear force, our equation is WLWTTFWD. This equation is given on page number 80. Now, why we have to multiply it with 2? Then we have to provide it a welding on both the sides. Okay, so for both the sides, our welding is provided. We have to multiply it with 2 value. Okay, now V is 200 into 10 raised to 3. 2 is constant. 220 is our length of weld, which is the summation of these two, and it is round figure 220. TT, it means our unknown value, because we have to check that our selected throat thickness, which is 4.2, is find out from assumption of minimum size of weld is feasible or not. Now FWD is 158. Okay, so students, after putting all this value, our final answer of third thickness is 2.87 mm. Now, what is the equation of third thickness? It is 0 0.7 into S. So, we have to find out our value of S is 4.101 mm. Okay, now it means our selection, which is assumed in the range of 3 to 8.5, is feasible. So if we have to assume that our size of weld is 6 mm, but if we are providing a size of weld is 5 mm, then also it can resist a shear force of 200 kN and bending moment of 10 into 10 raised to 6 Newton into mm. Okay, so students, this is the end of our example number 2. Now, in the second example, mostly similar kind of calculations are there. So, let us start our second example. So, our second example is based on welded moment resistance connection. Okay, it means in this example, our shear force as well as bending moment is directly given. Okay, because as the name given, moment resistance, whenever in the question our moment resistance is directly given that, then you have to solve that example based on this method. Okay, so our second example is for ISMB 500 at 852.5 Newton per meter. Students, there is one mistake in your Atul Prakashan book that in the book it is 825.5, but there is no any section for 825.5 load. Okay, so it is 852.5 Newton per meter transmit an end reaction of 300 kilonewton and bending moment of 150 kilonewton into meter under the factor load to the flange of column ISMB 300 at 576.8 Newton into Newton per meter. It means our ISMB section 500 can transmit a shear force of 300 kilonewton and bending moment of 150 kilonewton into meter. Now a design of welded connection. So first of all, from steel table for ISMB 500, the width of flange, thickness of wave and total depth for both the section will be write down from steel table. Now, this type of example is visualized in the side and the junctions like this. Okay, so in this example, we have to provided this plate, top of flange plate, and we have to welded this portion. Okay, so this is a moment resistance connection. So as per given in the data, our force is 300 kilonewton and bending moment is 150 kilonewton into meter. First of all, we have to find out force on top plate. This is our top plate. So it is M by D, and you all know that moment is equal to force into perpendicular distance. Then moment is equal to force into perpendicular distance, then force is equal to moment by distance. Okay, so it is 150 into 10 raised to 6 divided by 500, so it is 300 kilonewton. This is 10 raised to 6. Okay, so students, after calculating all the data, our force on top of the plate is 300 kilonewton. Now we have to check that how much area required to resist 300 kilonewton. So first of all, our required cross sectional area is P by Fy into gamma m0. This equation is not given anywhere, so our P, it means we have to require to restrain this much force, so it is 300 into 10 raised to 3 divided by 250 into 1.1. It means if we have to resist this much force, then it requires 1320 mm square. Now we have to assume that our width of plate, this width of plate is 180 mm, then what is the thickness? So the thickness is d into d, in which our b is 180 mm. So the thickness is 1320 divided by 180. So it is 7.33 mm. It means if we have to resist this much force, then its length is 1320 mm, sorry, 180 mm, and its minimum thickness is 7.33 mm. So that's why we have to provide it a thickness of plate is 10 mm. Okay. Now the size of this plate which is provided at the top of the flange is 180 mm width and 10 mm thickness. Now how much welding is provided over there? So you all know that for 10 mm thick plate, our minimum size of weld, which is as discussed in the last example, that minimum size of weld is 3 mm and maximum size of weld is 8.5 mm. So again we have to assume that size of weld is 6 mm. Now you all know that there is two types of weldings, again shop welding and field welding. For shop welding, the design stress is 189, and for field welding design stress is 158 Newton per mm square. Okay, so we have to assume that field welding over here, you can also assume shop welding. Okay, whenever there is no any clarification in the exam. Now first of all, we have to find out that what is the minimum length of weld per meter length. So, strength of weld per mm. So, it is LW TT into FYW, sorry, FWD. Students, this equation is given on page number 80. This equation is in the form of FWD is equal to P by LWTT. So we have to find out and made a subject of P, then it is equation is LW into TT into FWD. Now LW means length of weld is equal to 1 meter, because sorry 1 mm, because we have to find out the strength of weld per meter length. Okay, per mm length. So it is 1 mm. TT means throat thickness, it is zero point 0.7 into S, and FWD is 158. So if we have to provide it 1 mm weld, then it can resist 663.6 Newton load. Now length of weld required is load by this. Okay, so it is 300 into 10 raised to 3 divided by 663.6. So we will get our answer 452.6 mm. It means our round figure value is 460 mm. Okay, so total 460 mm welding is provided over here, in which this length is 180. So full welding is provided over here. Then from 460, 180 is provided over here. Now how much welding is there? So it is 460 minus 180. So it is 280, from which 140 length welding is provided over here and 140 mm length welding is provided over here. So it is called side welding. So side weld is 140 mm on both the side. This is due to bending moment. Now for shear force, from shear force welding is provided over here. Okay, so for shear a length of weld is remain same, because the length is 300 into 10 raised to 3. So our provided length is 460 mm. Now 230 mm length welding is provided over here, and 230 is provided over here. Okay, so students, this is the end of our today's session as well as your syllabus of design of steel structure. Okay, so students, thank you.